Hello guys, I am Dr. Devendra Mishra, working as Assistant Professor in Chemistry at Bidla Institute of Applied Sciences, right? Also running this Tetrahedron Chemistry Classes channel, and here are the links available to approach me. Hello friends, welcome back to the Tetrahedron Chemistry Classes. So guys, in my coordination lecture series actually I didn't complete one or two topics which are actually quite important for your CSIR net and the gate examination point of view. So in today's class I am going to discuss that NEPHELAUXETIC effect, right? So it is difficult especially for me to pronounce that word NEPHELAUXETIC again and again. So I'll call this effect as the N effect. You should remember that particular point. So before going into the details, you should focus on this particular diagram. You can see these are the metal d orbitals, right? So you can see the orbitals which are actually along the axis, they belongs to the EG set, and for my convenience I have shown only dx square minus y square orbital. So this is dx square, this is dy square, okay? And in between these axes I have shown one lobe of the T2G orbital, that is dxy, right? So this is the case when your metal is free, right? And your metal could be anything from your first transition series or the first transition, second transition series, or the third transition series. It could be anything, okay? So what I want to explain here, you can see the lobes here. These lobes are quite small, d orbitals are quite small, and of course these d orbitals are having electrons depending upon the electronic system, whether you are having the D1 system, D2, D3, D4, or whatever the system you have, okay? So what happens guys when actually the complex formation takes place? So what, see, you can consider there is a ligand here, and again you can see, consider there is a ligand here. So all around the ligands are there. So when actually ligands are there and complex is formed, right? So when complex is formed, you can notice that the lobes of the d orbitals now actually they are quite bigger in size. That means their lobes are increasing in size, okay? So when actually this increased size is there of this d orbitals, so they easily penetrate into the ligand's orbital. So when the mixing of this ligand orbital and this increased lobe of the d orbitals of the metal ion takes place, right? So that means the electrons which were earlier present here actually now will actually have the more space to move, right? You can see this is the bigger lobe, and of course you will have the overlapping ligands here. So what actually happens here, expansion of the cloud, expansion of the d electron cloud takes place when the complex formation is occur, and this is all about and the NEPHELAUXETIC effect is all about of this, right? So you can relate this NEPHELAUXETIC effect by the expansion of the expansion of the d electron cloud. And see, this NEPHELAUXETIC actually it's a Greek word, and the meaning of that Greek word is the cloud expansion or the cloud expanding. So whatever this NEPHELAUXETIC effect actually explains, it explains the decrease in the interelectronic repulsion of the metal d electrons when the complex formation takes place, right? And when actually you see these orbitals are actually, when they are bigger in size, they easily actually enters in the ligand orbitals. So there is considerable overlap between the ligand orbital and your metal d orbital, and you know that when overlapping is occur, so it is the property of the covalent bond. So it is explaining the covalent character in the metallic in the your complexes, right? So this is actually the rough idea of your NEPHELAUXETIC effect. And here now you can see the heading which I have given to this particular topic: NEPHELAUXETIC effect and the covalent character of the metal ligand bond in the complexes, okay? So your N effect explains the decrease in the interelectronic repulsions of the d electrons on the complex formation, as I have explained to you, okay? So this thing is very, very important. And of course this N effect or the NEPHELAUXETIC effect is the indirect evidence of the existence of the covalent bonding in the ML bond of any complex, okay, right? And you can see when electronic repulsion is there actually, was there actually, right? See, since the size of the lobes are quite small in the free metal, so electrons are very close and the repulsion is very, very high. So when the complex formation takes place, then actually these orbitals actually move far apart and interelectronic repulsion decreases. So roughly 20 to 25% decrease in the electronic repulsions actually occurs when your complex formation takes place, okay? So 20 to 25% decrease in the repulsion, it's actually the quite the bigger value. Okay, this is something very, very important. And then finally you can notice here, under the influence of the ligands, okay, expanded d electron cloud penetrates into the ligand orbital, hence overlapping occurs. Now the electrons of the d orbitals more delocalized, and delocalization is the characteristic property of the covalent bond. So these are the points which I have already explained to you about the NEPHELAUXETIC effect. So this is the basic idea about the NEPHELAUXETIC effect. Okay, now how we can determine that N effect or the NEPHELAUXETIc effect? You can see here. Then there comes the very important parameter, which are known as the Racah parameter, and this Racah parameter is actually after the name of some scientist actually, right? So actually he was a mathematician and the physicist actually. So basically it's a mathematical calculation. Racah parameters is all about the mathematical calculation. Okay, but we don't need to go into the details of the mathematical calculation. We will understand that Racah parameter in the simplest manner. Okay, so how we can understand that Racah parameter? I want to explain this one. For this, you can see, guys, you can focus here on the this is actually the Tanabe Sugano diagram. Okay, and in the Tanabe Sugano diagram, this is actually the D3 system, and you know, when you have the D3 system, then this is actually the 4f term you will obtain, and this 4f term will split into the A2, right? And similarly you can see it is going at T1, and of course another you can see these are the term 4A2, then 4T2, and then your 4T1, right? So these are the three terms. However, other terms are also there, and you can see there is a difference between the lines actually. This is the energy difference. Okay, and this energy difference actually is due to the inter-electronic repulsions between the electrons, right? So whatever the term is there, that term will split actually, and during this splitting, whatever the difference between the energy would be there, it is due to the inter-electronic repulsion. Okay, and if you want to determine that extent of that repulsion, then you have to determine the Racah parameter. Okay, this is this actually you have to keep in mind, and your Racah parameter is best studied in your Tanabe Sugano diagram. Okay, now guys, you can see here in the, so you can see in the Tanabe Sugano diagram, different terms of the configuration have different energies due to the electronic repulsion, as I have already explained with the help of the example. Whatever I have explained, I have summarized in the points here. Okay, and the inter-electronic repulsion which causes the bending of the lines. So what is the meaning of the bending of the lines? You can see here, bending of the lines. You can see this line is going in that manner, this is going in that manner. So this is the bending of the lines actually. That then you can see the inter-electronic repulsion which causes the bending of the lines is expressed in terms of the Racah parameter, and Racah parameters are A, B, C. Three types of the Racah parameters are there, but for you can see the system for the same multiplicity, we know we need only one parameter, that is B. So, and we are interested in this B only. Okay, this will give you the inter-electronic repulsion. This is something very, very important, that B actually represents the DD repulsion, DD electronic repulsion. Okay, so actually these ABC are the empirical quantities, and you can find that quantities by see these ABC actually can be obtained by using the gas phase atomic spectroscopy. Okay, and you see the B represents the DD electronic repulsion. Okay, and this B is actually sufficient to evaluate the energy difference between the states of the same multiplicity. As I have explained, same multiplicity, whenever we have the same multiplicity, then it would be sufficient to determine the B. Okay, so this is the Racah parameter. This is as simple as, like, you can see it is very simple, but actually the student gets confused in this particular topic. It seems quite difficult for the students to understand this topic, and you actually not need to go into the very much details of that Racah, those Racah parameters. You only stick to that B actually. Okay, which gives the DD electronic repulsion. However, this A actually will give you the overall repulsion, whether it is in the ligands orbital, in the metal ligands, metal orbital, and the ligand orbital, and the, see, whatever the electronic repulsion would be there, it would be given by the A, total repulsion, and B actually give you only the DD electronic repulsion. Okay, this is the Racah parameter. Then after that there comes the very important point. This is the beta NEPHELAUXETIC ratio. It is called the NEPHELAUXETIC ratio, and that NEPHELAUXETIC ratio is what actually? It is B dash by B. Again, this is the Racah parameter B. This is the Racah parameter B. You know B is what? It represents the DD electronic repulsion. Only DD electronic repulsion. So B dash is the repulsion, DD electronic repulsion when the complex formation occurs, and B is the DD electronic repulsions when no complex formation takes place. That means free metal is there. Okay, when free metal is there, then you can see the repulsion is very high. In that case, the repulsion is very low. When the repulsion is low, definitely that beta would also be low. If this beta is low during the complex formation, okay, then B is also low, right? So when the B is low and this is high, so definitely this B will always have the value less than 1. This is something very important which you have to keep in mind, that beta is always, this ratio actually is always less than 1, because this actually B dash, that means the DD electronic repulsion, this would be actually minimum in case of the minimum in case of the complex formation. This you should remember. Okay, and the important point which you will note from here, actually, when actually the NEPHELAUXETIC ratio beta actually decreases, then NEPHELAUXETIC effect is increases. So what is the NEPHELAUXETIc effect? Effect is the expansion of the electron cloud, D electron cloud. Okay, so when this value goes down, so what is the meaning of the values goes down? Obviously this will actually increase. Okay, and what is the meaning of the increase of this one? That means this gives the expansion of the electron cloud. So when beta decreases, then NEPHELAUXETIC effect actually increases, and when NEPHELAUXETIC effect increases, of course the delocalization increases and the covalent character increases. This you should keep in mind. This is very important point, because see, NEPHELAUXETIC series which is given in the various textbook, actually it is given in the other way, and people understand that that series is according to the NEPHELAUXETIc effect. No, it is not according to the NEPHELAUXETIc effect. It is according to the NEPHELAUXETIc ratio, and that ratio is inversely proportional to the NEPHELAUXETIc effect. When it goes up, then it goes down. When it goes down, it goes up. This you should remember. Okay guys, this is very important point. Then after that, you can see here there are certain factors which can affect the NEPHELAUXETIc ratio. Okay, and see, remember, I am talking about the NEPHELAUXETIc ratio. Actually, I am not talking about the NEPHELAUXETIc effect. These two are the different. So as I already explained, if beta goes down, right? If beta goes down, then definitely your B dash goes down. So what is the B dash go down? You know, B dash is what? It is the electronic repulsion. Okay, when this value is low, of course the beta would low, because they have the direct relation. You can see here, beta is directly proportional to the B dash. When the repulsion decreases, of course the value of this decreases, right? And when repulsion decreases, then electron cloud expansion increases. This you should remember. Okay, so here you can also write one point here: electron cloud expands, increases. Okay, guys, so here you can see that when beta goes down, then the repulsion goes down. When repulsion goes down, then the NEPHELAUXETIc effect actually will increase. That's why they are the inversely proportional, as I have explained. So guys, now you can see this particular series, which is the NEPHELAUXETIc series, and this series actually you have to understand. So this series is given for the some ligands, right? And it is independent of the nature of the metal. Any metal you can complex with these ligands actually, right? So for this to understand, you should know the FAJAN'S rule. Okay, polarization. So I have made a very extensive lecture on the FAJAN'S rule. You can go through the FAJAN'S rule in my channel. You can write FAJAN'S rules by tetrahedron chemistry classes, so you will get this. Okay, so in that case, you can see, if you start from this one, you see this electronegativity for this is very high. This means the size of this is very small. You know, the F is quite small when compared to the I. Okay, so when size is very small, that means it is very difficult actually to polarize the electron cloud of this F negative. Polarization would be difficult for this one, right? When polarization would be difficult, that means it will not form any covalent bond. And you know, your HF is having the ionic character, maximum ionic character. Okay, so due to the smaller size and high effective nuclear charge, the electrons of the fluorides are not available to form the covalent bond. And when covalent bond formation would not occur in that case, that means the nepheloxetic effect would be low and your nepheloxetic ratio would be high in that case. So I have summarized the points here. You can see for F negative, due to the small size and your high effective nuclear charge, nepheloxetic ratio is quite high. And you know, the nepheloxetic ratio is inversely proportional to the nepheloxetic effect. When beta high, that means this ratio is high, of course the nepheloxetic effect is low. When nepheloxetic effect is low, that means the electron cloud expansion would not occur. Lowest cloud expansion would happen in that case. When expansion would not occur, that means there is no delocalization of the electron. And when there is no delocalization of the electron, that means lowest covalent character. If the particular metal form a complex with this ligand, then of course it will have the very low covalent character. It would be actually predominantly ionic in nature. Okay, and there would be no nepheloxetic effect, right? So this is the left end. Now if you focus here, this iodide, you can see it is the very bigger in size. When bigger in size, that means the electron cloud is readily available and it could be very easily polarized according to the FAJAN'S rule. When it is very easily polarized, that means it will form a covalent bond. When it will form the covalent bond, that means the delocalization would be very high. Electron cloud expansion would occur, and electron cloud expansion then occur. That means the nepheloxetic effect would be high for this one, but nepheloxetic ratio would be low for this one. Opposite of that fluoride here, you can see here beta is lowest. That means ratio is the lowest, but effect is the highest. Electron cloud is the maximum, having the maximum expansion. More delocalization and more the covalent character when the metal forms the complex with this particular iodide actually. So this, if you travel from left to right, then you will find covalent character actually increases from here to here. Okay, so if metal is forming complex with the oxalate and metal is forming the complex with the ammonia, then definitely that oxalate complex would have the higher covalent character and higher nepheloxetic effect, but lower nepheloxetic ratio. You should understand these things. Okay, so this is covalent character increases, right? Electron cloud expansion increases, nepheloxetic effect increases when you move here to here, but nepheloxetic ratio, if you write beta here, it goes down from here to here. Okay, this is very important to understand, and this can be easily understood by using your FAJAN'S rule. Okay, then again you can see the second factor which can affect the nepheloxetic ratio, which is, say, if the ligand is fixed. You can pick any one of the ligand actually. See, when metal is in higher oxidation state, so what is the meaning of that? When the electrons are not there, large number of electrons are not there, that means the effective nuclear charge is very high for this one. When effective nuclear charge is very high, it can very easily polarize any ligand. And see, in the light of the FAJAN'S rule, if it can polarize the ligand, that means it can form a covalent bond. When it forms the covalent bond, definitely the delocalization would occur. That means the nepheloxetic effect would be high for this one, but nepheloxetic ratio would be low for this one. So if you travel from here to here, you can see for metal, having the one oxidation state, it will have the higher nepheloxetic ratio but low nepheloxetic effect. Okay, when nepheloxetic effect is low, delocalization is low, covalent character is low, right? And electron cloud expansion is low. And from, if you move here to here, again you can see covalent character increases, right? Electron cloud actually expansion increases, right? And nepheloxetic effect increases, but nepheloxetic ratio decreases. Okay, and you can see here, if actually these two values are equal, this one and this one, beta dash and beta, if these two are equal actually, that means no covalent character would be there in the bond, and bond would be 100% ionic. But you know the 100% ionic bond is not possible in any case. There must be some covalent character in it. Okay, so in that case, if you follow that particular series, you can see here, if I have arranged for this particular metal ion which is in the highest oxidation state, it will have the highest. Okay, so if you see that series and if you compare this series with this one, then you can find this metal Mn is the highest oxidation state. That means it will have the highest nepheloxetic effect and lowest nepheloxetic ratio. That means the covalent character would be very high in that case. Okay, so however, it is not possible to explain each the role of each and every metal ion present in it, right? But this is given in the textbook, and you can see you can argue this rhenium is 4 positive. Why it is actually here? It should be at the right hand side in the table. So it is see, it is up to you. You can remember that particular series in some manner. You can devise any mnemonic for this, right? You can learn anyway, and if you don't know anything, then you don't need to worry about anything. You should focus on this series only. Okay, and by learning and by understanding this concept only, you will be able to solve the problem based on the Racah parameter. Okay, so you know that this is the formula for the Racah parameter. So if you have given this ratio or this value, then you can determine the electronic repulsion from the in this, and if you have given these two parameters, then you can determine this, right? So you can find 1 or 2 numericals in your textbook, which would be very simple actually. So I'm not going to solve those numerical. You can go through your housecraft book and your say Shaver and Atkins. So you may find 1 or 2 numericals, and see, one numerical is there in your selected topics in inorganic chemistry while by Wahidul Malik, right? So it is a good book to understand your coordination chemistry. Okay guys, so this nepheloxetic effect is actually quite simple, but people think in that manner. It is quite difficult. We cannot understand this. So all you need to understand is what the difference between the nepheloxetic effect and nepheloxetic ratio. Okay guys, so this is all about nepheloxetic effect. Okay, so if you like if you're liking the explanation, subscribe the tetrahedron chemistry classes and share with your friends also. Okay, and please don't forget to like the video. Okay, thank you very much.